Welcome to our next lesson on universal gravitation. Isaac Newton was able to find the force between any two objects called the force of attraction by using its mass of the two objects to find the following relationship. The force of attraction is equal to the universal gravitation constant multiplied by the two masses divided by the distance between those two masses all squared. Here's the breakdown again. M1 is the mass of the first object. M2 is the mass of the second object. R from 1 to 2 is the distance between object 1 and object 2. G is a constant, which is 6.67 times 10 to the power of negative 11. And the units are newtons times meters squared divided by kilograms squared. Again, this is called the universal gravitation constant. Let's try this relationship and apply it to an example. I want to find the force of attraction between two basketballs. Each have a mass of 0.65 kilograms and they are 1 meter apart. Force of attraction is the constant multiplied by mass 1 and mass 2 divided by the distance between those two masses all squared. Our universal gravitation constant is 6.67 times 10 to the power of negative 11. One mass is 0.65 kilograms, the other mass is also 0.65 kilograms, all divided by our distance between those two basketballs, which is 1, and then squared. So we're going to put this into our calculator, and you should get 2.8 times 10 to the power of negative 11 newtons. And that's our answer. Let's try a different question. This time we're given the force of attraction, and we know the two masses. So we're trying to find the distance between those two masses because it's asking about how close they are. So in this case, we know what M1 and M2 is, which is 50,000 kilograms. We also know the force of attraction, which is 200 newtons, but we're looking for R between 1 and 2, which is the distance between those two masses. So this is our equation. I'm going to rearrange this to solve for R. So that means I'm going to multiply both sides by R squared and then divide both sides by FA. And then I'm going to square root both sides because I do want to get R by itself. So we're just going to put in our information then and solve. G is 6.67 times 10 to the power of negative 11. Mass 1 is 50,000 kilograms, and we're going to have the same thing for mass 2, so I'm just going to write this squared all over FA, which is 200. Our final answer is going to be 0.029 meters. So this seems simple enough. What happens if we try to extend this into 2 dimensions? I'm going to draw a diagram for you, and our goal is we're going to find FA on the second mass. And I'm going to introduce 3 masses. This is mass 1, mass 2, and mass 3. Mass 1 is going to be 10 kilograms. The distance between mass 1 and mass 2 is 3 meters. Mass 2 is 15 kilograms. The distance between mass 2 and mass 3 is 4 meters. And lastly, the mass for the third object is going to be 20 kilograms. The first thing we're going to do is consider the relationship to find Fa on M2. So what we're actually calculating is the force of attraction of the second object, and this is how I'm going to denote it. Fa subscript 2. This is going to be Fa from 1 to 2 and Fa from 2 to 3, which means that I need to find Fa from 1 to 2, and I also need to find Fa from 2 to 3. So I'm looking at this portion and this portion. So let's find Fa from 1 to 2. That's g times m1 times m2 all over the distance between object 1 and 2 squared. So g is 6.67 times 10 to the power of negative 11. Mass 1 is 10 kilograms. Mass 2 is 15 kilograms. The distance between them is 3 meters, and we're going to square this. After this calculation, we should get 1.11 times 10 to the power of negative 9 newtons. And for our direction, this is going from the second mass to the first mass, so this is an upward direction. Let's look at Fa from 2 to 3 now. So that's g times mass 2 times mass 3 all over the distance between mass 2 and 3 squared. So that's 6.67 times 10 to the power of negative 11 multiplied by mass 2, which is 15 kilograms, multiplied by mass 3, which is 20 kilograms, all divided by 4 meters squared. We're going to get 1.25 times 10 to the power of negative 9 newtons. And this is going to the right direction just by looking at our diagram here from mass 2 to mass 3. Now moving on to the next part we need to do, we have an x and y component. So I am going to draw a vector diagram of what's occurring here. So to the right, we have 1.25 times 10 to the power of negative 9 newtons. And then upward, we have 1.11 times 10 to the power of negative 9 newtons. We're trying to find Fa2, which is the vector of this resultant vector. So that means I'm going to use Pythagoras to find that missing side of our vector triangle. So Fa2 then is the square root of 1.25 times 10 to the power of negative 9 squared plus 1.11 times 10 to the power of negative 9 squared. This is going to be 1.67 times 10 to the power of negative 9 newtons. We also need to find the direction because this is a vector which has a magnitude and direction. This is tan inverse of 1.11 times 10 to the power of negative 9 over 1.25 times 10 to the power of negative 9, which is opposite over adjacent, which is 41.6 degrees. Now we can state our final answer. Fa2 is 1.67 times 10 to the power of negative 9 newtons at 41.6 degrees. And just by looking at our vector triangle, this is going to be at north of east. Let's do another example. It's a continuation of that picture I drew before. But I'm going to draw the picture again just so you have it. Mass 1, mass 2, mass 3. Mass 1 was 10 kilograms. Mass 2 was 15 kilograms. Mass 3 was 20 kilograms. The distance between mass 1 and 2 is 3 meters. The distance between 2 and 3 is 4 meters. Now our question here, we're going to find the force of attraction acting upon mass 1. So note, just like the first example we did just above, when we consider this, we have to consider the force of attraction between mass 1 to mass 2 and the force of attraction between mass 1 to mass 3. How that's going to look like is something like this. So we have to look at that vector to figure out what FA13 is. Okay, the first thing I'm going to do though is find FA1 to 2. This is a downward direction. G times mass 1 times mass 2 all over the distance between those two masses. Which is 6.67 times 10 to the power of negative 11 multiplied by 10 kilograms multiplied by 15 kilograms divided by 3 squared. This is 1.11 times 10 to the power of negative 9 newtons. And remember, this is a downward direction. Now we're going to find FA from 1 to 3. So that is that purple vector that I drew in there. It looks like this. We can definitely still find the magnitude of this vector. So this is going to be 6.67 times 10 to the power of negative 11 multiplied by 10 kilograms multiplied by 20 kilograms, and we still need to find that distance between 1 to 3. I'm just going to quickly draw a triangle on the side here. We know this distance is 3, we know this distance is 4. This is one of our special triangles, so we know the hypotenuse should have a distance of 5. And if you didn't know that, I can always use Pythagoras to find that your missing side is 5. And then after we do this calculation, it's going to be 5.34 times 10 to the power of negative 10 newtons. And our direction here is south of east. We can actually be more specific about that by finding the angle. Because it's south of east, if I were to draw it in an XY plane, we're looking for this angle. And this would be 4 along the horizontal and 3 on the vertical. So if I want to find theta, it's going to be tan inverse of 3 over 4, which is 36.9 degrees. And then we can insert that in here to be more specific. That is 36.9 degrees south of east. Now the next thing I'm going to do is organize all of our information from A and B into its X and Y components. Mainly because FA13 is a vector that has an X and Y component, so we should break that down. I'm going to do this in a chart just like how we've done it before. Okay, so FA12 is strictly downward, so we don't have an X component, but you do have a Y component. Because it's going down, make sure you include a negative. And then for FA13, we have the magnitude and its direction. So if I want to find what that's going to be in the x direction, if you think about our picture here, if I want the x component, I'm going to use cosine to get this one. So that's 5.34 times 10 to the power of negative 10 cos 36.9. Then for my y, it's going to be sine to get my y, which is opposite over hypotenuse. That's 5.34 times 10 to the power of negative 10 sine 36.9 degrees. And remember to include a negative in the front because it is going down, it's going south. Now we're going to add up our components together. So in total for my x component, I just need to calculate 5.34 times 10 to the power negative 10 cos of 36.9, which is 0.427 times 10 to the power of negative 9. Then I'm going to add the two components for my y together, and I'm going to get negative 1.43 times 10 to the power of negative 9. Our next step is to find FA1, which is the resultant of those two components that we just found. This is also saying that we're going to do vector addition, so that's FA12 plus FA13 to get FA1. So we could draw this out if you wanted to. So it's positive in the x direction, negative in the y direction. We're looking for this one here. So I'm going to use Pythagoras. You have 0.427 times 10 to the power of negative 9 squared plus negative 1.43 times 10 to the power of negative 9 all squared, which is 1.49 times 10 to the power of negative 9 newtons. That's our magnitude. Now we need to find the direction, which is this angle in here. You just use tan inverse, which is 1.43 times 10 to the power of negative 9 all over 0.427 times 10 to the power of negative 9. Notice that 10 to the power of negative 9 is just kind of cancel out anyway, so you don't need to insert that in your calculator. But this will be 73.4 degrees, and our direction is south of east. So this is our magnitude, and this is our direction, and that is our final answer.